Okay, so I'm going to quick talk you guys through the logic diagram for what's going on when we're using the Turnigy 9X transmitter, the receiver, how that relates to pulse width modulation, interrupt service routines, how that all interfaces with the Arduino Mega 2560, our PWM motor driver, and how we're using that to control a remote controlled tank. So we'll jump right in. The user moves the thumbsticks, that's the first step, these thumbsticks here, up, down, left, right, for our tank controller. Up and down on the left side control the left motor, up and down on the right side control the right motor. And that Turnigy 9X transmitter receives those analog inputs. They're analog because they're in real time, and converts them to RF digital information and transmit it to the Turnigy 9X receiver module. Now this receiver module is paired with that transmitter, so it's always listening for signals from that transmitter. And it takes those signals and it converts them into a PWM signal and outputs them on the associated channels. So this one here is channel 1, and channel 1 pin is here, channel 2 pin is here, and so on. So it takes it and says, hey, this channel, so when we think of channels, channel being say one axis, so thumbstick up or thumbstick down for left thumbstick, that is one channel. Thumbstick left, thumbstick right for just the left thumbstick is another channel. So on a thumbstick you have two channels. So we have two thumbsticks, so there's 4 channels, and then there's one button, so that's our 5th channel. And what it does is it converts that analog information into some digital information, which is a pulse width. And it says that, hey, we read that the transmitter had the left thumbstick all the way forward, so say left thumbstick is mapped to channel 1, just for example. And it's all the way forward, so the width of the channel 1 pulse would be, maybe 2,000 microseconds. 2,000 microseconds in width is all the way forward, and 1,000 microseconds in width is all the way back. So it takes that information and converts it to a pulse width modulation, and then the Arduino Mega we have programmed to read that PWM signal via interrupt service routines. So an interrupt service routine is basically you can think of it like you're sitting at home waiting for the pizza delivery driver, and the pizza delivery driver, he's going to show up sometime, in the next maybe 15 minutes, and you could either get up and go and check to see if he's there every 5 seconds, or we wait until we hear the doorbell. In this case, our doorbell is the rising edge of one of these pulses. So we're sitting there watching our movie, and hey, all of a sudden we hear the doorbell. Hey, it's a rising edge. We go, we check the door. So in our case, we're checking the width of a pulse. And then after we check the width of the pulse, after we get our pizza, pay the delivery guy, we go back to our normal routine. So on the falling edge of the pulse, we go back to the normal routine. And then in the normal routine, so we just measured, this pulse, the width of that pulse, and then we go back to the normal routine, which is say, hey, let's determine how this pulse width relates to thumbstick positions. And as I mentioned earlier, all the way forward 2,000 microseconds, all the way back 1,000 microseconds. So we write an algorithm for the controller to take over that mathematical operation to let us know what those thumbstick positions are for each of the 4 channels associated to the thumbsticks. For our controller, the left thumbstick is mapped to the left motor, up and down, and the up and down channel for the right thumbstick is mapped to the right motor, and then the left thumbstick left and right movement is mapped to turning on relay 1, and the right thumbstick left and right movement is mapped to turning on relay 2. Anyways, so our Arduino measured the width of the pulse and determined what those thumbstick positions are. Now what do? We want to tell our motor how to respond. And in order to tell our motor how to respond, we need some way to interface with it. So a common way to control the speed of a motor is to vary the voltage. That is basically the only way to vary the speed of the motor without changing the load or applied current or other more complicated things. So we want to change the voltage to the motor. How do we do this? With our good friend pulse width modulation. So with pulse width modulation, we can say we want a duty cycle of 50%. That means it'll be in the on state for 50% of the time and the off state for 50% of the time. And so if we have a 24 volt signal and it's on half the time and off half the time, what's the average voltage for the motor? Well, if your answer was 12 volts, you're right. If your answer was anything else but 12 volts, you're not right. Basically, the average value sets that motor speed because we're switching it so fast that the RMS voltage, the average voltage to the motor is that effective 12 volts, which means we will be moving the motor at 50% of its rated speed. And basically the huge advantage to PWM is that even though we're saying that, oh, hey, the motor's only seeing 12 volts, in actuality, it's seeing a peak of 24 volts and a minimum of 0 volts, which means we still get the full voltage applied to the motor during the on times, and then the off times we're just off. So we send a PWM signal to this motor driver saying, hey, we want you to be on maybe half the time, maybe all time. If it's, the thumbstick's halfway in the forward position, we'd want it, on half the time. So it's switching really, really quickly, so it's on half the time and off the half the time to control that motor speed. And then we also set 2 different pins here, which change the direction of our motor. So that motor driver is turning off at a really high frequency, turning on and off at a really high frequency, based off of the output from this Arduino Mega microcontroller. And then you, the user, watch the tank respond, and then you adjust your thumbsticks accordingly. Say you're going over an obstacle or you're turning, so you move them again, and then this whole process starts back over at moving the thumbsticks, and then proceeds the same way as discussed previously.